Please go
Okay. So, hi everyone. I'm Nandana Dilip, a Civil Department freshie and the manager of Alumni Relations Cell at IIT Madras. So, today we have Professor Satyanarayanan Chakravarthy with us for our Guru Talk session. So, I welcome sir to this awesome session, and he's a professor from Aerospace Engineering Department at IIT Madras. So, I welcome you, sir.
Thank you very much, Nandana. Thank you all for getting onto this talk that I have to give. My topic for this evening is taking deep tech from lab to market. So let us get going. I have to start with an apology. Due to some last minute unexpected clash in timings with another engagement, this talk I would actually have to restrict it to 30 minutes. We will try to take a few questions, but I would like to answer most of the other questions in the chat box by mail subsequently. So this is another event that has actually been rescheduled for whatever reason on reimagining Tamil Nadu, where I have to talk about what we're doing. So without further ado, let me talk about what we are doing at what we call as the National Center for Combustion Research and Development at IIT Madras, or NCCRD for short, where we have a whole bunch of startups and projects and ideation that has been going on for the last 4 or 5 years, maybe. And I would like to first of all acknowledge that this work is actually not possible without the support of a large number of faculty, students, research scholars, entrepreneurs, and the employees of those startups, the IIT Madras Incubation Cell, the government support agencies like DST, SERP, MHRD, DRDO, ISRO, etc., and many private companies, and also financial investors in these startups. And this does not cover the academic research or the research sponsored by or for the consulting external funding agencies that we do here. It's primarily about startups, product development, technology development, and ideation, and so on. And we would like to actually pitch this as the most happening place for deep tech development in the world. And I would like you to take a call on that yourself as you go through the rest of the talk. I will walk you through a very quick list of what we have, and that's actually about a laundry list of about 18 items. And then we will actually pick a few to showcase what we are doing, and then make my final remarks. The first one I will talk about is what we call as Agnikul, which is doing 3D printed rockets for mini launch vehicles. We have the E-Plane company that is providing urban aerial mobility solutions in terms of a electric plane and also for regional and domestic aviation. This is also something that we can repurpose with optical guided air launch missile for distributed airstrike. We have been doing a bunch of surveillance, survey, mapping, inspection, and multi-copter drones, and also hybrid aerial vehicles for long duration flights of those applications. One of those, one such drone is like a very large drone that is meant for pesticide spraying in farms, which is what we call as an agricopter. I and one of my colleagues at the NCCRD also are faculty advisors to the student group called Avishkar Hyperloop, with which we are developing the most cost-effective Hyperloop development in the world with a very, very specific program towards commercialization. We have a startup called Galaxy, which is into multi-sensor remote sensing satellites with edge computing AI. We have a micro gas turbine startup called Aerostrovelos, which is developing a solution for hybrid EV trucks, gensets, and microgrids. We have a startup called X2 Fuels and Energy that is into making crude oil from unsegregated municipal solid waste. We have a startup called TAM90, which is into cold chain with phase change materials. We have another startup idea called Lidust, which is into optical sensors for pollutant emissions in chimney stacks, particularly even with wet scrubbers. We have an ideation and research happening on aluminum air batteries, which are rechargeable high energy density energy storage solutions with some IP there. We are into actually hydrogen generation, which is aluminum based, which is the cheapest form of hydrogen production. Based on this, we could also actually use this with human urine to make sustainable toilets, or also repurpose it for water desalination as well. And these are actually net energy positive. processes. We are into coal gasification, and we have optimized for high ash Indian coal, where India has very vast reserves, so that we can actually use this for hydrogen production or methanol or urea. We are developing what actually started as a COVID project on PAPR devices, actually is now being repurposed for wearable air conditioners. That's a huge energy saver to improve India's productivity. We are also actually trying to repurpose a bunch of medical devices based on our fluid mechanics and laser diagnostics expertise into coming up with smaller handheld devices that can enable virtual hospitals that can take an ICU to a patient's home. And finally, we have plans for a hypersonic aircraft which can actually take passengers from Chennai to San Francisco in 4 years, which we would want to develop in the next 10 years. So with that laundry list, what I will do is I will just spend about a couple of minutes in about 4 or 5 such ideas to give you a flavor of how the research done in the lab is being pushed into market. And these are actually very, very sort of, what should I say, high-tech devices or products that we are looking at coming out of our center. So the first one that we are talking about is Technical Cosmos, which actually has shown that we can do the most integrated single-shot 3D printed rockets, and we have actually fired them over long duration to reach steady-state thermal conditions and so on. And this has actually been, so the left-hand side, if you now look at this kind of a cross-cut in this picture, that essentially is what we are showcasing as the research that motivated this product. So the research that we actually were doing, and we're still doing at the Combustion Center, is a collaboration with GE and a government-funded, co-funded project on developing 3D printed gas turbine full annular combustors. This for micro gas turbine applications. So what used to be about 20 different parts is actually now 3D printed into just 3 big parts that are assembled, and we have a huge rig that is doing a full annular rig test under realistic conditions of high pressure and high temperature. Now, and then we have run this combustor with burning fuel over extended periods of time. Whereas in the rockets, you actually need to run this only for about 8 to 10 minutes at a time, and then it's like a single use most of the time. And of course, we are planning to do recovery and reuse at later stage. But but the pressures are higher, the temperatures are higher than in a aircraft gas turbine. So we have to go to in-kernel. So we have a picture that shows you the 3D printed rocket, and the picture, the other 2 pictures on the right-hand side are about the firing in the test bed that we have developed. So all of these things are actually planned to be taken into a 2-stage rocket vehicle, which is capable of carrying 100 kgs of payload. And this is a hugely modular rocket where the maximum configuration that we have come up with is about 7 such rockets that are in the first stage in a clustered manner with the gimbaling for thrust vectoring and all of that. And the same rocket actually will take its place in the second stage. And of course, the remaining the length of the rocket is filled with composite overwrap pressure vessels that are used for storing the fuel, or the tanks that are storing the fuel and oxidizer. Right. So with this modular rocket approach, we can now actually do a plug and play kind of a configuration where configurations which are essentially going to allow us to have a very, very flat cost curve down to about 30 kgs of mass in terms of cost per kg in US dollars of the payload, whereas the market price is actually something that keeps climbing up as you go to smaller and smaller rockets. So this is the problem that is being solved by Technical Cosmos adopting the 3D printed rocket approach. And very recently, they have actually got the 3rd round of funding of about $11 million. Again, one more thing that I want to emphasize is something like about $10 million is actually 1/10 to 1/15 of the cost that it takes for anybody else abroad to do a very similar job. And we are actually doing much more superior than what they are doing with these fully 3D printed single shot pieces of rockets with hardly any assembly parts to be made. Very similarly, on the E-plane company, which I'm doing, we have the most compact electric VTOL air taxi in the world, which is just about a 4 meter by 4 meter kind of dimensions. And that essentially means that it's less than 2 car parking lots worth of width in which this aircraft can land and take off, right? And we are also actually pushing this to be flying at a very, very low speed. Because you have wings, it can go to very large distances, like about 200 kilometers or so in a single charge. So the question is, how do we make this happen? How do we have like very compact wings, the opposite of what you would have a glider? You will have very long wings that is going very slow, or if you have a fighter craft, it will have very compact wings that it can fly fast. So we have tracked this by the kind of research that we do, which is patterned after NASA's distributed propulsion, where the propulsion is actually now distributed into smaller propellers in front of the wing, is what they had done. What we are actually doing is a different version of it, which is for VTOL applications, specifically using the VTOL rotors and distributing them around the wing in order to generate a large amount of lift and thereby enabling the wing to be compact. So this is, again, an IP that we have cracked that is pushed into a product development. In fact, this particular IP is what we call as targeted research to solve a particular problem of what a very compact, slow-moving, long-distance vehicle that is required for urban aerial mobility. So the other thing that I want to point out, just like the 3D printing that has become like a level playing field for Agnicol, composites manufacturing has actually become extremely commonplace in the Indian context, where we can actually do all these kinds of ribs and longerons and all of those structures of the aerospace, and actually get very good, very well polished surfaces and so on. So it's now possible for us to actually make world-class quality aircraft with very little money. Again, the kind of money that we are raising over here is going to be 1/10 to 1/15 of what the rest of the world, the companies are actually doing for aircraft that is not as good as this. That's the point. So it's not just like we are trying to copy something else. We are actually doing something superior at about 1/10 the cost. That's it. So the frugality here is not just a cost arbitrage that we're talking about. So the third example that I would take is something that I'm actually pretty proud about, because when we started the Combustion Center, it didn't really have a chance to talk about the Combustion Center itself, which is actually now a $30 million or about a 200 crore kind of facility, which started out with about 46 crores of money from the government about 9 years back. And we built this 5-story building thanks to IIT Madras supporting that particular development. It's a very unique building that's been built with all the utilities that are embedded in the walls, and everything was planned right from the beginning, right before the foundation. So with that kind of a very, very superior world-class facility, which is like the world's largest as well, we are also actually mandated to embrace certain grand challenges, combustion of practical importance. And one such grand challenge we have tackled is that of gas turbines that are used for power generation, like the ones that GE or Siemens or Alstom or those kinds of companies have to do with, like very large gas turbines that generate something of the order of about hundreds of megawatts. Now, the problem they were actually facing was they had to face very stringent pollution norms because they are land-based, but for which reason they wanted to burn very lean in fuel so that they will keep the temperatures low, but that was also leading to a huge amount of combustion instability. So the grand challenge that we embraced was to come up with one particular combustor configuration that's good in both the pollutant emission norms to be met, as well as to have very, very stable combustion. And we again picked NASA Glenn's lean direct injection and tried to improve upon it significantly into what's called the swirl mesh lean direct injection that we have patented. And that we have pushed into a startup called Aerostrovilos that is making a microgas turbine. So the right-hand side picture, we actually see a proof of concept of a 100 kilowatt prototype, which actually can be shrunk to even about 2/3 of its size. And this will actually be 1/10 of like an equivalent diesel genset, but at the same cost. So the cost has been disrupted primarily because of a huge part load efficiency that we can accomplish with this lean direct injection combustor that we have developed. And the other important thing about it is it's hugely fuel agnostic. So currently what Aerostravelos is doing is to come up with a turbine-based generator on board a EV truck to come up with a series hybrid electric vehicle solution with a very small battery pack, but essentially a electric vehicle chassis and a powertrain in the front end. But you have multiple tanks that will allow this vehicle to be fueled with any fuel that's available on the highway. Could be diesel, or it could be liquid natural gas, or compressed natural gas. Going forward, it could be hydrogen, and so on. So this, we believe, is actually going to allow us to go towards the direction of multi-fuel future, which we are transitioning into, and stand in good stead over the next couple of decades or even more, because particularly when you now go to hydrogen, the emissions problem is not there. And with hydrocarbons, the kind of emission levels that we are having is about 1/10 to 1/100th of the current norms, which means that it will stand in good stead over the next couple of decades as well, right? So it essentially allows the truck owner and the truck operator to pick whatever fuel that makes economic sense for them, and the numbers actually stack up extremely well in favor of this particular application. So the last such example that I'd like to give is also something that I'm extremely proud about, which is done by my colleague Vinu from chemical engineering, who works out of the Combustion Center. And this is a startup called, and what we do here is to convert waste to crude oil. The crude oil, X-crude, because this could be any waste, it could be any kind of, well as the most important interesting, attractive option here is unsegregated. So we are essentially challenging the notion of being prevailing in the rest of the world, where we have been that you need to put only the fuel into a particular engine, otherwise the engine will not work. And we are now challenged. So far, we are now coming around to actually make an engine that will actually work with any fuel that the user could be completely agnostic of. And similarly, we are essentially challenging the notion you have to actually even segregate waste in the first place. And it's not required for you to do this. You can actually deal with unsegregated waste, and we will produce crude. Now, what do you do with this? We are not solving the full problem of having to make a biopet. That would not make economic sense. But the moment I actually produce crude, I have an existing infrastructure into which I can blend this crude, existing refineries, and then let them take over this. And we have a cost benefit analysis by which we can price this crude comparable to the petro crude, right? So then it makes huge economic sense, because we can start progressively importing less and less of crude from outside the country and save a lot. Now, going further, we also think that we don't need to necessarily refine this at all kerogen that contains all the kerosene and so on that you would want still in a refinery that you would not go to, and just completely get rid of that process, take this kerogen and put it in the Aerostravelos engine, and it will start actually working, which essentially means that we can get rid of importing oil, we can get rid of refineries, we can get rid of we can do local power generation, we can power lines and all of that stuff. So this is the kind of future that we envision with what we are doing. And similarly, if you now look at the electric planes, we can get rid of airports, we can actually go from door to door. So we don't need all these big infrastructure there and stuff. And similarly, when you now look at Agricool that we talked about, we can actually launch it out of trucks, and all we need is a barren land. We don't need like huge launch pad kind of infrastructure and so on. So that takes us to my concluding remarks that I would like to stop with. And we have coined a word called Defra Structure that is the underlying essence of this emerging deep tech lab to market story. So what exactly is this, right? We challenge the notion that we need large infrastructure for a country to develop. This is the fundamental point that we would like to make. High-tech products that are small but produced in large numbers can easily compensate for the large infrastructure that we are so much used to thinking about from the Western world so far. And small rockets, small planes, small engines, small waste-to-fuel units. That's what we have actually shown, right? So question is, large scale is not about big things, but could also be about large number of units of small things. And we can easily compensate that way. This allows us to actually develop ourselves into a modular, on-demand, distributed, affordable technology that can enable development rapidly at a pace that we can afford, right? And so we are not really always challenged saying, okay, you are going to be always chasing the rest of the world because you're actually following their template. We completely change the template. So this is what we call as democratizing technology. And this is not inferior tech at all by any means. It's actually, if at all, it's actually very superior technology that we're talking about 3D printing or composite materials or batteries. And that's what so we can actually, the other thing about this smallness and this high tech that we're talking about, it's possible to be developed out of academia and their startups. And we have clearly shown, case after case where research can be pushed into these products, and it should have market sense and business case and so on. So what's actually allowing this to happen today is metal 3D printing, carbon composites, batteries, simulation capabilities. And these are all essentially offering now a level playing field for startups to take on big tasks with small products. And this is a way by which premier institutions can directly contribute to nation building and its economic growth in a sustainable manner. And engineering and technology is all about product development first, right? So we want to essentially say academic institutions can directly get into the job of product development today with all of this stuff and push the economy forward and increase and contribute to the GDP, right? And the research that we have to do then can be done on the problems that need to be tackled to improving these products further and further. So we have now a good idea why we need to be doing research in the first place, because we have these products that we are developing. Those will pose research problems. We work on those research problems. So the entire ecosystem now gets built around product development and economic development. So this is the whole idea that we want to do, right? So this way we can actually ensure that our students will stay back in our country because this is the market that they would serve, right? So this is the overall ecosystem that we are trying to build over here. Thank you very much. I would be very happy to take any questions.
An awesome session. Okay, so let's move on to the Q&A session. So audience can put on their questions in the chat box. So, sir, the very first question is, what was the basic motivation behind this research?
Right. To be honest, actually, we start off normally, right? So we had the largest combustion group in the country, and the government actually found sometime in the mid to late 2000s, according to the 9th plan or something at that time, that combustion was at a crossroads of an energy transition in terms of alternate fuels that we have to have, as well as the environmental challenge where we were talking about global warming and so on. So they solicited us to, set up a combustion center. We made a proposal for 46 crores. They allowed us to set this up, and we started building very big setups that are done at fairly good scale for that the industry really takes a look at, right? Otherwise, combustion is one of those multi-physics, multi-scale problems. Unless you do it at some scale, it is not relevant to the industry. So the moment we actually started doing industry scale problems, we now started thinking, hey, why can't we actually develop our own products? And that's the motivation for the whole thing.
Great, sir. So I guess that's with the Q&A session.
Yeah, I see a comment there that says, please come back and give a longer talk. I think if the unfortunate that I have to actually stop today with a shorter talk, but I think I just want to leave you with the idea of not only what we're doing, but also like a recurring theme, as I could say.
So we have a few questions.
Sure.
So how about the economies of the scale for the strategy?
Sorry, repeat that.
So what about the economics of the scale for the strategy?
Oh yeah, so that's the other thing that happened, right? So the moment we said that we will actually develop our own products, let's say for example you pick this gas turbine. I have this technology that can actually get into a GE or a Siemens combustor, and they can, do well with it. But the old economy and the large economy, right? They are actually clay-footed. I can actually say this in public, right? Everybody will agree with me. For them to actually change their combustor strategy will take long years for them to actually figure out that they can do this, right? So they will not do it. So that means I have to actually push it into a startup. Now, having a technology is different. Having a product is different. Having a business case is different. All these things have to be stringed together. So unless I see a business case with a product into which I push my technology, I cannot have a startup. So all these startups have very, very robust business cases. It's not as if like they work at the small scale or a large scale. We have to work at particular scale, right? And we have to make it happen. And that's being possible with things like 3D printing and disruption in composite manufacturing, all of that stuff I said, because it becomes extremely cheaper now to do this.
Okay, so we have another question. Does a startup at NCCRD have to be incubated at IIT Incubation Center?
Yes. That's primarily because most of it is done by faculty, and I think as faculty members, we will incubate at the incubation cell.
Okay, so we have one more. When do we think these R&D works can be commercialized?
Oh, they are attracting a lot of investor interest already, right? So, for example, Agnikul has actually got, as I said, close to about $15 million worth of investment. E-Plane, we got $1 million last year, close to $1 million last year. This year, we are actually at the cusp of raising another $4 to $5 million. So, the investor interest itself indicates that there is a go-to-market strategy within a line of sight, right? So, all of these things are essentially going to come out in the next couple of years. Agnikul is actually planning to launch by end of the second half of 2022. E-Plane will do its first product, first prototype liftoff by first quarter of next year, and so on. So they're all around the corner. And Aerostovilos truck is expected to happen by first half of next year. X2 fuels will commercialize again next year. So 2022 is like a big year for us.
Okay, so one more question based on the topic of EV truck. Is the final drivers electrical or not?
Right. So that's a very interesting question because it's an extremely flexible architecture, right? So as batteries get better and better, it's possible for us to actually shrink the gas turbine even more, right? So that's a hybrid that we are looking at. Right now, we are essentially saying with the kind of costs that we have for the batteries and their very poor energy densities, it's sufficient to have a thin slice of a buffer, and then the front end is all EV powertrain. So but effectively, what's running it is this micro gas turbine on board, which is a power generation. There is not even a talk about range anxiety we have to worry about because it's conventionally from the fuel tank. Drive into a petrol bunk and fill up your diesel, or if you have a LNG station or a CNG station, you can do that and so on. So it's exactly the same thing as how you would normally practice, but the front end is EV.
Okay, sir. So one more question. What are the plans regarding hiring young talents, regardless of their experiences and degrees?
Okay, bad question to ask me. I think the young talent today can actually learn a lot of these things just online. Okay, and I think it's possible that when you go to grad school, you can actually drill much deeper. That is based on choice of the student to learn deeper and so on. But it's important to actually allow the students to learn whatever is required with mentorship and configure these kinds of products. That's probably a Defra Structure in academia that I would propose.
Okay, sir. So I guess that's it with the Q&A session.
Thank you very much.
And thank you, sir, for sparing your valuable time here.
I would like to take questions by email if that's possible.
Okay, sir. Sure.
Thank you. Thank you very much.
Thank you, sir. Thank you very much. Thank you, audience.